Okay, everybody, let's get to rank correlation. All right, so we just got done with Pearson's linear correlation. Now, Pearson's linear correlation is an awesome test statistic. However, it does have its limitations. It can only be used for data that is linear in nature, okay? But what about patterns that are not linear in nature? There's patterns everywhere in life that are not linear. What do we use for those type of patterns to test to see if those patterns are significant or not? We can use a test called rank correlation. And rank correlation was developed not by a dude named Pearson, but a dude named Spearman. Okay, and Charles Spearman to be specific. And so it's called Spearman's rank correlation coefficient. And this is the definition. Instead of R, it's R sub S. All right, that is a capital S right there. That's just an R, little sub S. It's cursive hyphen S. All right, so how do you calculate R sub S? Well, imagine we're studying the number of hours studied for a test versus the grade on a particular test or exam. Okay, and here's the number of hours studied, and here's the grade. The way you calculate Spearman's rank correlation coefficient is you rank the data individually. Yes, you rank the data from low to high. And the lowest number, let's start with the X's. The lowest number is a 2 hours studied, okay? That gets a rank of 1. But then the next number after 2 is 5, but there are 2 5s. Now here's the kicker, I should say. This 5 and this 5 would get ranked 2 and 3. But since they are the same number, you average the ranks of 2 and 3, and they both get ranked 2.5 and 2.5. That is huge. If you can understand that one concept, you can do rank correlation. That's it. So far, we've ranked 3 numbers. So 1, 2, 3. So then the next number, which is 8, would get a rank of 4, and so on. 9 would get a rank of 5. 10 would get a rank of 6. 11 would get a rank of 7. 13 would get a rank of 8. And 15 would get a rank of 9. And last but not least, 18 would get a rank of 10 because there's 10 numbers. By the way, n equals 10. N still represents the numbers of pairs of numbers. Then you rank the y values from low to high. 33 is the smallest number in the y values, so that gets a rank of 1, then 2, and so on and so forth. So you're not necessarily comparing the raw data to each other, you're comparing the ranks to each other. The 5th ranked number is compared to this 4th ranked, all right? The 2.5 compared to the 2nd. So do the ranks correlate to each other? That is the big thing right there. The highest number here is correlated to the highest number here. That's very correlated. The 9th ranked number here is correlated to the 9th ranked number there. Very correlated. First and first. This is a very correlated set of data right there. Okay, but you're not comparing the raw numbers, you're comparing the ranks. If you wish to compute R sub S by hand, feel free to look at all this and calculate it, and you'll get an R sub S value of 0.97. Would you wish to do that on your calculator? Of course you would. Let me show you how to do it on your calculator. I'm going to put these ranks, not the raw numbers, but the ranks into L1, and these ranks of Y into L2. And if I share my screen with my calculator, like a good chef on a cooking show, I have it already prepared. Stat, enter. There are the ranks of L1, the 10 ranks of X, and the 10 ranks of Y. So what am I going to do? I'm going to go to Stat. I'm going to go to Calc. And I'm going to arrow down to lin/reg. Now, it's not linear regression. It's linear correlation. It's rank correlation. But because I put the ranks in, I can do this. Hit enter. Yes, X's are in L1. Y's are in L2. Go to calculate. And look what pops up. R is 0.97. Let's go back to my notes. R is 0.97. So the bottom line, all right, in L1 and L2, if you put the raw data, you're going to get Pearson's. You're going to get Pearson's R value. If you put in the ranks, into L1 and L2, you're going to get Spearman's R sub S. That's the bottom line. You do the exact same thing. You put the X's in L1, the Y's in L2. But if they're the raw data, you get Pearson's linear R. If you put in the ranks, you get Spearman's rank R sub S. That's it. The procedure is the same. Just like in linear correlation, R is used to estimate rho. With rank correlation, R sub S is used to estimate rho sub S. Okay, so let's do a hypothesis test and call it a day. With reference to the preceding example, where we had n equals 10 and R sub S is 0.97, test the significance of this value of R sub S at the 0.01 level of significance. So look at the hypotheses, always the same. Rho sub S equals 0 versus rho sub S does not equal 0. There is no correlation between hours studied and grade versus there is a correlation between hours studied and grade. Look what word is purposely not there. Do you see the absence of the word linear? Yes, the word linear is never used with rank correlation. Significance level 0.01. The R sub S value is, just copy it. Look at the assumptions. Okay, now this is your very first glimpse of something called a non-parametric test, which we are going to talk about in a couple hypothesis tests. What is a non-parametric test, hypothesis test? It's a test with fewer assumptions, fewer assertions that need to be met. Look at these assumptions. It's a random sample of paired data, and the data can be ranked. That's it. If you could remember from the last video, what were the assumptions for linear correlation? The Y populations had to be normally distributed. The Y populations had to be equal variance. Both populations had to be normally distributed. That's a lot of baggage. A non-parametric test versus a parametric test has much fewer or much less restrictive assumptions. All right, the decision rule. We're going to reject HO if R sub S is greater than R sub S with n pairs of data alpha over 2 level versus vice versa. So n pairs of data, that's an n, is 10 pairs of data. The alpha over 2 level is 0.005. So let's go to the R sub S table. First of all, the R sub S critical values of Spearman's rank correlation coefficient R sub S always assumes two-tailed. So I'm going to go to 10 for n. I'm going to go to 0.01 for the alpha level, because even though it's 0.005 in each tail, the alpha level is still 0.01. It always assumes it's a two-tailed test. So 0.794 is right there. So reject HO if R is greater than 0.794, or if R sub S is less than negative 0.794. It says, note, Spearman's table always assumes a two-sided test. If the test for some reason happens to be one-tailed, you go up one level. So in other words, let me go back. If alpha is 0.01 and it's a one-tailed test, use the alpha 0.02 column. If the alpha level is 0.05 but it's a one-tailed test, use the alpha 0.10 column. That's what that means. Okay. The computations, R sub S is 0.97. Did it on our calculator. You could just say done on calculator. Now wait, 0.97 is much bigger than 0.794. So we are going to reject HO. We're going to accept H1 that there is a relationship. There's a correlation between hours studied and grade on the exam. Notice that the R value is positive. So because R sub S is positive, we say that there is a, now 3 magic words, not 4, but 3, a significant positive correlation. Notice it's 3 magic words and not 4 magic words. Why 3? Because the word linear is not used. Believe it or not, we're done with the test. That was really quick, wasn't it? Done. All right, so what are some of the advantages of R sub S versus R? It allows us to analyze some data that can be ranked but not measured. So, you know, ranking movies from 1 to 10. Okay, it can be used to detect relationships that are not linear. This might be the biggest one right here. Okay, not all relationships are linear. A lot of relationships are not linear, and a rank correlation test can determine correlations that are not linear. Okay, number 3, it could be used where some of the more restrictive requirements of linear correlation are not met. For example, the non-parametric does not require normality of both populations. Yeah, so in other words, the assumptions are more watered down with a non-parametric test. Number 4, just like R sub S is a decimal between -1 and +1, and the scatter plots look exactly the same. -1 is a perfect scatter plot downward, +1 is a perfect scatter plot upward, and R sub S equals 0 is just scattered all about. Don't worry about number 5. That's when n is greater than 30. Don't worry about this. Yes, it's true. I mean, not all this is factual stuff, but you don't have to worry about it. Okay, that's it, everyone. All right, good job. Questions, ask.